Okay, so we're going to begin the presentations for the seminar and to share information. We chose to do a first session today on different aspects we haven't looked at yet. We've talked a lot about lenses, Fresnel, wave theory, but Fresnel is more than that. Fresnel was also an engineer, a graduate of the Polytechnic School, and who started out in the civil works profession. And so we thought it was important that we should show other aspects, and in particular the things around the lens. There's the mercury bath, for example, which enables the lens to rotate correctly. Mercury today is something that raises a certain number of issues. Can we leave it in place? Does it pose a danger? Can we not find other solutions? And we're going to look at that with Yves-Marie Blanchard, who is going to replace Michel Cousquer for this presentation. After that, we're going to look at the structure itself of the lighthouse with two presentations by academics, one from France and one from the UK, who are going to talk about the different stresses on the lighthouses themselves. And after that, lighthouses have a function that they fulfill, but they are also part of our heritage and need to be shared as such. And so we're going to have a presentation about how we promote lighthouses and how they can be shared with the broadest possible audience. Usually I speak for a very long time, but I'm going to stop there so that we can stick to time and that you can get off for your visit to Cordouan, which I'm sure you're all looking forward to. So I call upon Yves-Marie. He's hiding over there behind the curtain. And I don't have a label for Yves-Marie, so he'll just have to settle for being called Solange for the next 15 minutes. Hello, everybody. So the green button is to move forward. So I'm going to talk to you about a slightly more technical subject, but there'll be plenty of photographs to keep it interesting. And so one of the things Fresnel did is that he invented his lens, which was a technological breakthrough. But he also thought about the issue of how to rotate it, because at the time they were on the rollers, it was difficult to rotate the lens. And so he shared the idea that it might be possible to place it on a bath of mercury, as mercury is very dense, and that the lens could therefore float and turn almost without any effort, as at that time they didn't have much in the way of motors. They used a counterweight to rotate it. However, today mercury poses questions and problems for the environment. And in France, we're trying to see how we could perhaps change this technology of rotation on a mercury bath. And here you have a map showing you the issue of mercury in France. You see that all around our coastlines we have lighthouses. And in France, when we did, the aim is to have all these navigation aids all around our coastlines. Thanks to Fresnel and Fresnel, we have this line of lighthouses all around the coast that at any time a mariner should be able to see two lighthouses in order to know where they are. So you have lighthouses about every 20 kilometers, 10 nautical miles. And right the way around the coastline, we have about 100 lighthouses which are still using mercury baths. It's not at all the case in other countries. Often it's 10 times fewer. In most other countries, they've been working for a long time to switch from mercury to other technologies. But in France, we continued using mercury because it was reliable. It didn't require much maintenance. And we had a lot of lighthouses with mercury. So in 2016, we still had 85 lighthouses with mercury. Now we've started switching over from mercury baths to other solutions. Now the figure today is probably closer to 80 rather than 85. So that's what I'm going to present here, what we're doing on this issue. So what are we seeking to do? Quite simply, the mercury is used for three types of application. First of all, the rotating screens. Here you have a photograph from Cordouan Lighthouse, and here it's a screen which rotates and acts as a mask around the light to create the flash. And this is so there is one flash every 4 to 5 seconds, 1, 2, 3 flashes, and so that's the rotating screen. This rotating screen at Cordouan is still on a mercury bath, but we're looking into how to replace it. Another application is the rotating contact. Sometimes the light source needs to rotate, and to avoid the electric wire being twisted around it, we use a contact which is in a bowl of mercury, and as it rotates, it maintains the electrical contact. And you have a photograph there. And then the third application, and the most important one here, is the mercury bath, a sort of tank on which the lens floats, and the lens can vary from about 100 kilos up to some in tons. So mercury really is very effective there. We can rotate the lens with just pushing it with a finger, and also that means we use less energy. We can use solar panels, etc., etc. for the energy. And so these tanks need to be replaced for several reasons. First of all, for environmental reasons. If mercury overflows, it could fall into the sea. And also for reasons of health and safety at work. Because in hotter environments, the mercury can evaporate and could reach a certain concentration in the air. So to get rid of this mercury, several solutions have been considered. First of all, to do away with the rotating screens like the one we saw at Cordouan, the easiest solution is to have a flashing light. So we have the light which goes on and off rather than rotating the screen around it. Another technique is to reduce the range slightly and to use an industrial lantern like the one you see here, which is obviously much less attractive than the Fresnel lenses, but which does work. It has its advantages and some drawbacks. The advantage is that it's quite easy to use. The drawback is that it's quite expensive and isn't really respectful of our heritage. And the last thing is to try to come up with alternative solutions without mercury, often with ball bearings, to try to preserve our heritage. So, a graph here. Here, the graph shows the distribution of the mercury tanks depending on the focal distance of the lenses, so that means more or less the size. So you see here at 0.9, these are lenses with diameters of almost 2 meters, whereas the first column here, 0.15, has a diameter of about 30 centimeters. It's much smaller. So you see that this distribution tends to be concentrated on the 0.25, so 50 centimeter diameters, and 0.3, 60 centimeter diameters. This is where we have most of the Fresnel lenses in our heritage. And what we're trying to do is to keep the heritage aspect. It is important. Many people do feel a strong attachment to these lenses. Some lighthouses also receive visits And we want lighthouses to be visited because this is a way of opening up the lighthouse. It's good for the lighthouse too, and it also conserves our heritage and the civil engineering structures. So we would like to have similar characteristics in terms of lifespan. We don't want to have to replace this every 10 years. We don't want too much maintenance because going out to sea can be a complicated operation. There can be storms. There are questions of availability of different resources, and we also want to try to keep the structure of the lens. And we think that this solution is possible for lenses. The lenses we see here mainly on the graph, which represent almost 80% of the lenses which could be dealt with could use ball bearings. So a test was done at CEREMA, that's the research organization I work for. We did a first installation in 2019 at Bel Air Lighthouse in Reunion Island. Generally, we do this first of all in more remote places like Guadeloupe, Reunion or Martinique. This is interesting because first of all the environment is hotter, so there's more risk of the mercury evaporating. There are also problems of earthquakes which can pose problems. And then it's a way of seeing how it goes. So here you have a photograph of a tank that the CEREMA has designed. So it has the same appearance as the mercury bath that you find on site, like a sort of tank. And the ball bearings are placed inside, and we also put in an oil which is designed to last, to have a good lifespan, to keep everything well greased. And it works very well, in fact. So here, this is shown in the premises of the CEREMA laboratory, with two tanks with the ball bearings in an oil bath which are being tested and which we try for a time before they are installed on site. And so we're going to see in the photographs afterwards, perhaps in more detail, so an example. And as we are here in the region, we thought we would show this installation of a system with ball bearings at the Contis Lighthouse in the Land region to the south of where we are here. And so you see a photograph here, top right. You have a cross-section with two systems of ball bearings, one for centering, one supporting the lens. And some people call this the chip pan because it has the shape and we're putting oil into it. So when we arrive, we have to take all the measurements to see where we're going to do the installation and drill the holes. Then we disassemble we remove the panels. The difficult thing is draining the mercury from the old tank. How do we get the mercury out of it to be reused, or once it is recovered, it's handed over to a private company for reuse. And here we see that we have some of our staff from CEREMA who have all the necessary protective equipment with the masks, the gowns. There's a tap, a faucet that needs to be opened to drain the mercury. One thing I forgot to mention earlier is that in the specifications we wanted everything it wanted to be possible to transport everything by hand. One of the problems we have in lighthouses is we can't always bring in big, heavy machinery to transport tanks. So it's better to be able to dismantle things into small parts, small components, and to disassemble or assemble on site to avoid needing heavy lifting machinery. And once the mercury has been drained and the lenses and former tanks have been removed, we have to install the new tank. Here once again you have some photographs from the inside with the system with the ball bearings. And then at the end we set everything up again. Here you have a photograph showing the motors. Now, as I said earlier, mercury is something very efficient, which enables the lens really to move, to rotate very, very easily. But with the ball bearing system, in fact, there's very little difference. It works very well too. And it was possible for us to keep the same motors with the ball bearings as the ones we had with the mercury. So here there are two engines, a main one and a backup engine. One of them operates 70% of the time, the other about 30%. So if one breaks down, the other one can take over. So the lighthouses and beacons require very technical solutions with a long lifespan and which are easily repaired. And so there you have it, with the light on. Thank you very much.
Donc, je pense qu'on va prendre.
Okay, so for any questions on this subject, we'll take them now. Would anybody like to ask? It's a rather specific subject. He really doesn't want to take any questions. He wants to wait till the end of the session. Okay, so I'll call the next speaker. We'll keep the questions for later. And we have Nathalie Domed, who is going to present a study on the Île Vierge Lighthouse, and I'll hand over to her straight away. I just wanted to ask some questions.
Good morning, everybody. First and foremost, I'd really like to thank the organizers of this conference who are giving me the opportunity to present research work that I supervised in Toulouse in partnership with, let me see how I move this forward. There we go. In partnership with Cerema in Brest and Nicolas Fadi for several years. Now, to come back to the title of this presentation, I'm going to talk to you about the Île Vierge Lighthouse and climate action. I'm not going to talk to you about optics. And I just want to show you some of the Fresnel competences that maybe we don't think about. To begin with, I am going to describe to you what the Île Vierge Lighthouse looks like and why we undertook a 4-year research program at the lighthouse. So let me just start by describing the lighthouse to you. That will be simpler. Okay, I can see the screen now. Sorry, I couldn't see it before. I can see it now. All right, so Île Vierge is a very small island at the northern tip of Finistère in Brittany, in France. You have a picture on the right-hand side. You have 2 lighthouses. You have an 1845 house and a lighthouse that was put into service in 1902. It is the highest stone lighthouse in Europe. It is 82 meters high. You can see at the bottom on the right-hand side a photograph from the inside with the staircase, which is over 300 steps, and the stairwell then takes you all the way up to the top, to the lens, which is on a wall, a peripheral wall, that we call the base wall. The room, the keeper's room, is just below the machines at level 6550. We can see the figures approximately on the diagram you have here. It's been a listed document since 2011. It is made of granite, which has been taken from the island itself, and a stone from Brittany, which is called Saint-On. It's a lot like granite, but in fact it is not granite. The joints are cement mortar, and the lantern is puddled iron. It's a puddled iron framework. So why were we contacted by CERAMA? Because initially my profession is I'm a civil engineer, so I do research in civil engineering. Why was I contacted to do research on this lighthouse? Well, because the Île Vierge lighthouse is actually in rather good condition, but there were a number of pathologies, problems that were observed at the top of the lighthouse on this wall, which is the masonry wall that is a support for the lantern. So you can see here on the photograph that there are people walking there on the top of the lighthouse, and they're walking around this wall where we can observe cracks, and you can see the cracks here on the picture. And the cracks are on the entire height of the wall here. The cracks are really at the same place as the metal posts that support the lantern and that enter the wall on to the internal face side of the wall. So the fact that we have, well, structural disorders with these walls supporting the lanterns, that happens quite often. But in this case, we were contacted because we could not understand the origin of the cracks. So in 2017, we started our research program, civil engineering program, to understand the origin of the cracks, and this led us to start with historical research in the archives before we started working more on the civil engineering aspect, and maybe make hypotheses on the causes of the cracks. So some of our hypotheses, well, the first one was that it was simply the iron in the lantern. Well, the iron had corroded. So because of the corrosion, there was rust, and that gave rise to the opening of the cracks. But in fact, in 2017, repair work was done on the lighthouse, and that showed the posts of the lantern, and we saw that the corrosion was in fact very shallow. It was superficial, and that the inside, in fact, of the masonry was in good condition. So the corrosion of the iron was actually not the source of the cracks, the cause of the cracks. The next most logical hypothesis was the wind, because saying, okay, we have an 80-meter high lighthouse out at sea in a region where, of course, we have storms. So the most logical thing would be for the wind to, when it pushes on the lantern, to create openings and therefore cracks. So that is the first thing we explored, and that led us to look at a historical overview. So the first thing I asked myself was, in the 19th century, did we calculate the tower, and did we take the wind into account when we calculated the height of the tower? This led me to search in the archives, and there were many, many archives, luckily. So lighthouses and beacons kept all the texts from the time, all the letters ever written. The engineers at the time at lighthouses and beacons asked themselves many questions because they were aware that they were building the highest lighthouse ever built. And so they asked themselves questions about the calculation methods. And this is where it becomes very interesting when you're doing research, because they discussed many things between this is how some are doing it, this is how others are doing it. There were many letters, and all of these letters were kept, and they provide very valuable information on the methods for design of lighthouses in the 19th century. Now, just to try to sum up a few of the conclusions of the historical research on how engineers, in fact, took into account the action of wind on a lighthouse. And this is where I found out that Augustin Fresnel had played a key role in the history of civil engineering, despite the fact that he was known only as the founder of a founding role in optics. But you know that back in 1825, the mission of Augustin Fresnel was to build the Baleine lighthouse, and he asked himself how to provide theoretical calculations to check the stability of the lighthouse. So he started working on research done by John Smeaton, a very eminent leading scientist in the 18th century. In 1746, at the Royal Society of London, John Smeaton presented the table you see here on the left-hand side, where the first column shows the velocity of the wind. Then you have the force of the wind, and then the common appellation of the force of wind. So Smeaton is the first one to understand that the pressure exercised by wind is proportional to the square of the speed, of the velocity. And he came to the conclusion that in the case of hurricanes, which is the last line in the table, you have a speed of 45 meters per second. Augustin Fresnel used these scientific results and said, well, I'm going to calculate the tower of lighthouses with a speed of 50 meters per second, which corresponds to a load of 275 kilograms on a flat plate, so flat plate pressure. And this was a founding act on his part, because this value of the load has never was questioned, in fact, at any time throughout the 19th century. And the first calculations in civil engineering that were used by Gustave Eiffel, for example, for towers or for bridges, these first regulations kept the same value of 275 kilograms per square meter. Now, where he had an even more important role is that he then explained and he defined, in fact, a method for calculation. So without going into advanced mechanics, you have a diagram here with what I represented in yellow, a symbolic tower. So when a tower is square, we understand that the wind applies to the tower. You have the global force of the wind, which corresponds to the pressure per square meter of the face that is open to the wind. So the diameter and height of the tower. But when you have a cylindrical tower, the engineers of the 19th century did not know how to calculate the force of the wind. And there, Fresnel actually came up with a genius idea. He said on a cylindrical tower, the force of the wind is only 2/3 of the force that you would have if the tower was square. And as we've already said, Augustin Fresnel did not live very long. But his brother, Léonard, took over, and Léonard drew up all the calculation methods invented by his older brother, and he created a method. So I'm not going to go too much into the mechanics of it, but he explains how you take into account the self-weight stabilizing moment and the rollover moment due to wind, and he created a safety coefficient which needed to be at least equal to 4 as a dimensioning criteria for a tower. This method was developed by the Fresnel brothers. It was taught and applied until 1920 on all the lighthouses built in France and exported throughout the world at the same time as lenses. Now, to continue on the Île Vierge lighthouse, the engineers, well, we come back to the end of the 19th century, around 1896, they said, well, how can we have such a high lighthouse that would not suffer from oscillation when the wind starts blowing? Because we knew that this would, of course, the mercury tanks could in fact overflow if that happened too much. So we created the first oscillograph, which measured the period of oscillation of the lighthouse. And in 1905, it measured a period of 0.775 seconds. And I found this in the archives. Now, the question I asked myself with my researchers, colleagues, we said, well, today, what are we going to find if we calculate the lighthouse in 2020 with today's codes and today's standards, which are European standards? So in this table, you have a summary. In the middle line, you have a middle column, you have the results of the Fresnel method, and on the right-hand side, you have the 2020 Eurocode method results. So we see that for wind speed, Fresnel had said it was 50 meters per second. The top speed, the peak speed calculated with the European standard is 53 meters per second. The total wind load with the Fresnel method is 140 tons. The total with wind load is 75 tons with the European method, but you have to add an increase, a 50% increase, which means that you reach 113 tons. So Eurocodes, in fact, totally validates the Fresnel method, which was created over 150 years before. So the difference is only about 20%, which is not a big difference for this type of work. Now, the period that is measured today is exactly the same as the one measured in 1905. So we conclude that there is no risk of resonance, and globally that the lighthouse is stable, it is safe, and there is no problem in the structure related to wind. Now, to come back to our cracks and our crack problems. With CEREMA, we can say the only thing that we know that is happening in the lighthouse is to implement monitoring. And we implemented monitoring using anemometers that you can see on the photograph on the right-hand side at the bottom to measure the wind at three points, in fact, at the top of the lantern. Then we also had sensors to measure the variation of the opening of the cracks around the lighthouse, and also, so that was displacement. And then we also had temperature sensors, because there was a hypothesis that the problem was related to temperature variations on the wall. We carried out measurements over a 2-year period. We gathered results every second for the first 10 minutes of each hour. So I repeat, every single second for 10 minutes every hour for 2 years. So to tell you that we have a huge Excel spreadsheet, we have a database with we had approximately 20 sensors, and we measured for 2 years. So we have a huge database, and that is where our knowledge as researchers comes into play, because we do a statistical analysis to see how the 3 factors come together. So wind load, temperature variations, and opening of the cracks. So very simple to come to the conclusions. I'm just going to show you this curve, which shows vertically the crack opening and the temperature variations on the horizontal level. And you see the variations. You see 2 clouds that are aligned here in terms of the data on the graph. So we see that there's a correlation from one factor to another. So the crack openings are totally correlated with the temperature variations. So where do these temperature variations come from? Over the 2.5-year period, the temperature on Île Vierge was on average between 6 and 18 degrees Celsius, with a downward trend, in fact. Whereas, of course, with everything that we're hearing about climate change, I expected an increase. No, in fact, there was a slight downward trend of 0.2 degrees Celsius. Inside the lighthouse, the temperature varied very, very slightly, 10 degrees in the winter and approximately 20 degrees Celsius in the summer. But the temperature variations outside the wall, of course, that is, the variations are significant. It can be -5 degrees in the winter, and we can have over 42 degrees in the summer. And the temperature varies constantly all the time from morning to evening in every season and all year, so year-round. And what we observed, we saw a thermal gradient at a given point of 20 degrees between one side of the cylindrical wall and the other side of the cylinder. And this thermal gradient varies all the time, which means that the wall is constantly subject to flexion throughout the day. There are effects. The essential part of the variation of the crack opening is cyclical. In fact, things don't get worse. They just go back to the starting point and start again. But there is constantly this ovalization effect of the cylinder. This variation every hour, every year for hundreds of years, well, it creates what we call a thermal fatigue phenomenon. So the stone actually experiences fatigue localized at the anchor points. And this is what, in our opinion, triggered the opening of the cracks and continues to allow these cracks to develop and come back, develop and come back. So in conclusion, I would say first and foremost that this research really showed me the founding role of Augustin Fresnel in the history of civil engineering, and not only of optics, and in the calculations for civil engineering structures in relation to wind, because it is his hypotheses, in fact, that were kept for over 150 years. And we had to wait for the progress of aeronautics, the aeronautical industry, and knowledge of turbulence, in fact, for his work to be added to. But that was 150 years later. The lighthouse itself does not suffer from wind or from corrosion. It suffers, in fact, from temperature variations. Fortunately, these phenomena come up in cycles, so I'm not worried for the future of the lighthouse. These conclusions that we have found can be generalized to all the lighthouses that we work with. We also observed that the values and the temperatures that we measured are higher than those that are indicated in the European standards. And this is also a result which is important because all the bridges along the coastline of Brittany are calculated with the same European standards. So we had questions about that, about the European standards, so I'm happy with that as well. Well, thank you very much for your attention. All right, now, thank you very much, Nathalie, for that very interesting approach to enhance knowledge of Augustin Fresnel and his work. And now I will leave the floor to Alison Raby, who will tell us a little bit about the Stormlamp project.
Ça marche pas. Ah non, mais on m'a interdit. Vous avez bien compris là.
You understand that I was told that we could not have questions for now. So we'll have question time at the end. So just maybe write down your questions, and we'll be able to ask them at the end.
Ouais.
Merci. Bonjour. I would also like to thank the organisers very much for this opportunity to talk about the Stormlamp project to you today. Stormlamp is an acronym, stands for the structural behaviour of rock-mounted lighthouses at the mercy of impulsive waves. And this is a project that we conducted in the UK and Ireland over a number of years, about 3 years ago and back to 10 years. So I'm Professor Alison Raby, and I'm from the University of Plymouth. This is what Plymouth looked like many hundreds of years ago, a drawing from the archives, and we are a maritime city in the southwest of England. And you can see a number of old vessels there. So just off the Plymouth coastline is the famous or infamous Eddystone Rocks, which was the location of a number of significant shipwrecks over hundreds of years, with a loss of many lives and also an economic loss too. This was the first lighthouse that was put on the Eddystone Rocks. This was designed by Henry Winstanley in 1697. Very ornate structure. This only survived for about 5 years before a storm in 1702, and Winstanley was on the lighthouse when it failed one winter's night. This is in fact the third lighthouse. This is the Smeaton Tower, and you've heard about the civil engineer Smeaton in the previous talk. This lighthouse now is on Plymouth Hoe. It's the icon of the city of Plymouth. But this was taken down, it was constructed in 1759 and was dismantled in the 1800s because the rock on which it was built was starting to fail. So on the rock next to it, there became the Douglas Tower, and I'll talk a little bit more about that structure in a moment. So this work was done with the UK and Irish General Lighthouse Authorities, and it's good to have some representatives here today. I won't tell you too much about them because you probably know more about them than I do. But there's a question about why we should keep these rock lighthouses, and it was good to hear from the director earlier to talk about how we need to have these visual aids to navigation. But we do have satellite navigation and we do have modern lighthouse beacons, so why are we so interested in our rock lighthouses? Well, here's a good reason why. This is a photograph of the Mir space station and some damage that were caused to the solar panels with a collision. And in 2009, there was a collision between a communication satellite and the Cosmos spacecraft, which resulted in both of them being destroyed. So GPS is not fail-safe. The motivation for the GLA's concern, on the right-hand side, that's the previous Eddystone Lighthouse. And these are excerpts from the lighthouse keeper's log. Talked about in the 1800s a particularly violent storm, considerable motion of the cylinder glasses fixed in the lamps, and the tower appeared to jump as if resting on an elastic body. Something from the Bishop Rock Lighthouse, further to the southwest, with a report they were awoken by a severe wave impact accompanied by a loud booming noise. So pretty terrifying. But that was actually in 2014. So this was from a maintenance engineer who was on station during a storm. And in 2013-14, there was a sequence of 20 very large storms that hit the UK and the surrounding region. With climate change, there's predictions of increase in the sea level. So if the waves are riding on deeper water, then they will be hitting the towers higher up. And so back in 2010, we were contacted by Trinity House originally. The University of Plymouth has done lots of field work on more generic coastal structures, and they commissioned us to look at loading on the Eddystone breakwater. We have line of sight from the university campus out to the Eddystone Lighthouse, so we could communicate with it fairly readily. Following that successful Eddystone project, we put together a much larger project. University College London did the structural analysis. University of Exeter did some of the field work, and at Plymouth we managed the whole project and looked at the hydrodynamics. So we were particularly interested in the wave aspects. So we did some field modal testing, which I'll speak about now. Okay, so this is on top of the Bishop Rock Lighthouse, I think. And these are accelerometers that are placed on all the different levels of the tower. And then we shook the towers. So we went to different locations. We took our shaker equipment, shook the towers, and measured the vibrations at the different levels. And you can see from this map here the locations of the lighthouses. So Fastnet for the Irish Lights, up to Skerryville, we didn't actually get to at the time, but we went to Dubartak, and off the southwest peninsula we looked at Bishop Rock, Longships, Wolf Rock, Lehanois and Eddystone again. So we shook the towers and we also looked at the measurements from the wind. And the key findings were that the inclusion of a helideck structure on the top of the towers, which is fairly unique amongst the lighthouse authorities, the inclusion of those helidecks actually changes the structural response and the modal mass. So that was an interesting finding. But also with the data that we have, we can now work out from an inverse modelling what the size of the wave must be to create the vibration that we can measure. The long-term monitoring, we did this on 2 towers, the Wolf Rock Lighthouse and Fastnet. This is data along the bottom from the Wolf Rock Lighthouse, and you have a graph here showing a number of spikes, and those spikes correspond to the maximum velocities for different storms. A different number of storms there: Storm Ophelia, Storm Brian, Storm Dylan, etc. And so from those velocities we can calculate what the accelerations are and what the displacements are. We also have on the Wolf Rock a camera system. We have 2 cameras that are pointing in a slightly different direction from each other. We can get some photogrammetric information from that, so we can work out what the size of the wave is. Because we only have a limited amount of power on the lighthouse, we have to switch the system on and off. And we have had problems with remotely operating the cameras, but we do have some good data now. And we worked with Dr. Alvisa Benetazzo and Filippo Bergamazzo from ISMAR at CNR. Here are the cameras on the side of the helideck structure. So you can see here a very nice photograph where the lantern dome has obviously been removed and the helideck structure is constructed on the top, and this was done from the 1970s. The findings, well, from the velocities you can calculate the acceleration, and the acceleration occasionally exceeds 0.2 g. So that is in fact equivalent to a small earthquake. So it's not surprising that the lighthouse keepers were relating it to earthquakes. Now on the structural analysis. So we did 3 types of structural analysis. I won't go into too much detail, but bottom left is limit analysis. And there, force is added at various different elevations and an increasing force. And then the mechanism that will give failure of the structure is noted, and that can be plotted as a graph. In the middle is the finite element method, and that's where the whole structure is considered to be a monolithic structure, just one piece of stone. And then bottom right is the discrete or the distinct element models. And there, actually, it models the precise stones of the lighthouse. So the UK lighthouses are constructed by interlocking blocks, interlocking horizontally and interlocking vertically as well. So this discrete element model looks at the individual blocks and can calculate the stresses and strains of those. For the most comprehensive analysis, we did a discrete element analysis of the rock tower and then a finite element analysis of the helideck on the top. And we were able to identify some of the locations. Can I use this pointer? Yes. Some of these locations of the high stresses. So at the bottom of some of these bars. And we did the modelling with projections of the increase in wave climate over the next 50 years. And this can be used for operational reasons and inspections. And in fact, we've just been involved with redesigning the Bishop Rock helideck. Won't dwell on that. So the hydrodynamics, this is a photograph from the University of Plymouth Ocean Basin. And we did some modelling of the wave climate over the next 50 years. We did physical and numerical modelling of the waves interacting with the reef. And we started with a very simplistic representation of a cylinder on a simple foreshore structure of different angles. So we went 1:1 all the way down to a 1:5 slope. We did that at 1:81 scale. We then went 3-dimensional into our coastal basin, and then we went to a larger scale and we represented very accurately the bathymetry in that location. So I'll just take you through a few of these setups. Trinity House had their vessel, the Galatea, do some of the offshore bathymetry work, and a smaller vessel coming closer inshore. And then we sent a drone out there. Well, we had a drone out there, which then got the topography information. So on the basis of this drone survey, we're able to digitally represent the tower, the exposed rock around it, and then connect that to the underwater bathymetry. We constructed the lighthouse with a 3D rapid prototyping system. I think we had 7 individual pieces. You can see a steel core to this, just connected to a load cell for measuring the forces and the moments. We also had accelerometers there to give us any movement information. Although it was a hydrodynamic investigation, we weren't doing a small-scale model of the actual structure, measuring the stresses that wouldn't be appropriate. And we had pressure sensors, so we could work out what the wave impact pressures were, as Natalie was describing their importance in the structural stability. Here's a little sped-up film showing the construction of the bathymetry. We have a moving floor in our ocean basin, so we can raise it up right out of the water, build our models, and then lower the floor again. So we have this ribbed system, and this is the lighthouse model just here. In a moment, we will see the floor descending. It's nice to see the technicians working very hard in the laboratory. They've nearly completed now. This was done over a period of about 2 weeks, I think. There we go. So it's being immersed in the water. And you can see the yellow lighthouse model. So this just shows you more of the instrumentation and then a cross-section through the tank. And here is a video now of the waves coming from right to left, going over the reef, and you'll see them breaking just offshore and travelling up the lighthouse. So we were measuring the pressures along that sensor line, measuring the overall forces, and measuring the size of the waves in different parts of the reef, working out the wave transformation. So the major findings from the experiments, we looked at pretty extreme waves, like the 1 in 250-year wave, and we actually found out that the measured force was less than 30% of the predicted force. Now, the prediction equations are not designed for this configuration because, in fact, there are no equations to calculate the force on a lighthouse. So we have to make simplifications, and this was for a monopile connected to the seabed. So we knew that the forces wouldn't be exactly correct. But interestingly, we found that the duration over which the force exceeds a certain threshold was 50 times as long as we would have imagined. So it's generally the force impulse or the integration of the force over time that gives you the displacement. So the fact that the force is imposed for a long period of time is of concern. Also, I think it's on this slide. Okay, so also the numerical modelling, we had a computational fluid dynamics model, and we used machine learning to try to extend the parameter space so that we can, for different structural configurations, work out what the best estimation of the forces are. But I won't go into that complexity now. So the important findings, in this location, there were going to be no significant increase in wave height out to 2067, we don't think, but it only takes a small increase in wave height to create a much larger force. The lighthouses are affected almost exclusively by broken wave impacts. As the wave goes over a reef, it causes the wave to break and lose some energy, but the duration over which the wave interacts with the tower is quite long. Also, the wave run-up can be 3 times the wave height. So in our experiments, for some of our waves, we could see that the wave actually splashed as high as the helideck structure. And for the Wolf Rock Lighthouse, we know that that is the situation because as engineers fly out by helicopter and try to land on the helideck structures after winter storms, some of the panels are missing. So they've been lost by the wave impacts and also the wind loading. We had quite a complex guidance document that the lighthouse authorities can use, and you can find out more on our internet site on the stormlamp.org.uk. And we brought together lighthouse investigations from a civil engineering perspective from Île Vierge. We worked with Natalie, La Jument Lighthouse, Morris Island in the States, a Norwegian tower that was affected by ice loading rather than wave loading, and the Gaprock Lighthouse in Norway. Now, just bringing this right up to speed, a few weeks ago, this was the Mazarine cargo vessel, and you can see that it interacted with the Wolf Rock Lighthouse, and some of you might have read about this in the press. So for a period of several minutes, this cargo vessel was actually in contact with the Wolf Rock reef before it rotated slightly and then drifted. It had lost its power. And this is a view from the RNLI, come to rescue any personnel if that was required. And you can see this cargo vessel right next to the Wolf Rock Lighthouse. So it was stuck there for several minutes. Now, on this particular day, I was down at the Trinity House depot picking up some acceleration data that had just been flown off the lighthouse. So a day or two later, they flew back to the lighthouse and got more of our accelerometer data back. So we were able to see the impact of this vessel against the lighthouse or the lighthouse reef, and then also to verify that there was no damage caused because the structural signature of a lighthouse was unchanged. This is the Wolfrott Lighthouse model as it now looks. So we got a little bit of money to paint the model, so it's a realistic representation. And we have a rotating lantern in there and a small-scale Fresnel lens also. So from time to time we use this for public engagement events. So thank you very much.
Alors, merci beaucoup à Alison.
Thank you very much to Alison. I found that presentation really thrilling and really followed on well from the presentation by Natalie. It reminds us that a lighthouse is a civil engineering structure which has been well designed in such a way as to resist over time despite modifications. What it also reminds us is that we have always used the best techniques of the times for these structures, and Alison showed us there all the digital models, etc., and the sensors, which, as used also by Natalie, and we have an ability today to process large amounts of data, which enables us to have very dense measurements. And in just 20 or 30 years ago, we had difficulty having that source of information. I'm going to be getting told off if I don't move on quickly, so I'm going to hand over now to Dave, but I'm not sure where he is. Oh, he's behind me. And he is going to be talking, taking us to Ireland to see how lighthouses are used for local development purposes.
Thank you. Good morning, everybody, and thank you for giving me the opportunity to talk to you all today. My few slides will be a little bit less technical than the previous talkers, but I'm delighted to see us mentioned in Alison's speech. My name is Dave Ward, and I work with the Commissioners of Irish Lights. I'm the commercial manager there, but as part of my remit, I look after the tourism product, which we know as the Great Lighthouses of Ireland. So today, I'd just like to maybe run through the story of the Great Lighthouses of Ireland with you, its promise to visitors, the model for delivery, and our vision for the future. So the Great Lighthouse of Ireland is our initiative as to how we bring our lighthouse heritage to life. And this morning's presentations, I think, have been very interesting to listen to, because the technology advancements and the history of lighthouses is what the general public actually want to understand. Lighthouses in the past, the present and the future. So Great Lighthouse of Ireland is a collaborative tourism initiative developed by Irish Lights. It was launched in 2015, and it delivers significant value both to us as an organisation but to also lots of other maritime stakeholders on the island of Ireland. It enables us to protect and share our lighthouse heritage. It facilitates the development of sustainable tourism in remote coastal parts of the island of Ireland, which is really important in the current economic climate that we find ourselves in. It contributes a positive impact on coastal communities from the perspective of social cohesion. And right now, the Great Lighthouse of Ireland, it represents 15 partners operating 21 visitor experiences around the island of Ireland, north and south. And that's made up of visitor attractions where people get to climb into the lighthouse tower, visitor accommodation where they get to experience the unique and bespoke experience of staying at a lighthouse in lighthouse keepers' cottages, but also boat tours around the islands that can interpret the lighthouse from the sea. And we have 6 more sites planned over the next 2 to 3 years. And it's a great example of a public, private and community partnership that's come together as a collective with a committed ambition. So in 2021, I mentioned it was launched in 2015, but things changed very rapidly. In 2021, we did a brand refresh where we looked at the identity and what was resonating with the public, and we realised that it was about more than just climbing into the tower. In actual fact, what people wanted was to embrace the elements out and around the lighthouses. So we came up with the new fresh and vibrant look, which we feel gives the brand a bit more longevity into the future. And it aligns well with recent research that our tourism agencies have done around the concept of outdoor activity tourism and the trends where lighthouse experiences now are actually beginning to move into the health and well-being space as well, not just sharing the heritage and the technology. So the model for delivery, Irish Lights began operating around the coast of Ireland over 250 years ago. But in recent times, advances in technology and automation that has been referred to this morning has opened opportunities to consider a range of new uses for existing physical infrastructure, and tourism development was the obvious option for a number of lighthouse sites in Ireland. If I look at the history and how it developed, so in 1996 to 2012, lighthouse tourism was in its infancy and was being dealt with very much on an ad hoc basis. But in 2012, Irish Lights took a more proactive and strategic approach and successfully secured EU investment of 2.56 million in an Interreg programme to renovate a number of surplus properties and develop an all-island lighthouse tourism trail. This funding enabled the refurbishment of 5 lighthouses located across Ireland's northern coastline, and also facilitates the establishment of what we now know today as the Great Lighthouses of Ireland brand and partnership. So it was launched in 2015. It represents a necklace of lighthouse properties right around the coast, north and south. And the brand partnership enables us to position lighthouse experiences as a valued tourism, heritage and cultural asset for the island of Ireland. As part of that investment, we also developed a suite of marketing collateral, a website. We have brochures like this that seem to go down very well. In the world of sustainability, we're trying to move away from printed catalogues and brochures, but brochures like this seem to just get grabbed up. People love maps, and it's a great way of promoting the various different sites around the island, all helping to build brand awareness and helping unlock collaboration opportunities with tourism agencies to attract visitors to the island of Ireland. Up to 2019, we had 45 journalists and media hosted, delivering over 1.75 million worth of equivalent advertising value in national and international publicity, including placements in such publications as the New York Times and National Geographic, demonstrating such a strong interest from the international media in lighthouse heritage. Partnership and cooperation. Partnerships are very, very critical and are key to the success of the brand partnership to date. As we all know, lighthouses have universal appeal and are located in some of the world's most breathtaking coastal landscapes, but they make perfect venues for unlocking a variety of partnerships showcasing local culture, history and indeed event hosting. I did have a little video, but unfortunately there's a technical glitch, so that video is available on YouTube, but I just couldn't link to it here, so I'm going to skip on. So the Great Lighthouse of Ireland has grown over the last 8 years, and there's a lot to celebrate. Our goal is to develop sustainable visitor experiences based around our rich maritime heritage, our culture, but using building blocks of people, place and partnerships. And we recognise that there are many opportunities to shape our future vision. So to deliver that vision, we identified a number of strategic priorities as set out here. So the digital development piece is really crucial in terms of how we engage with our customers, the marketing, promotion, partnership and alliance and sustainable tourism development. And we recognise the need to combine our efforts in these areas to ensure that the Great Lighthouse of Ireland delivers value for all partners, because I suppose one of the big lessons we've learned is that no lighthouse, when you open it up, if you don't have community support from around the local locality, it won't work. So as a central agency based in the city, away from the coast, we've learned that through automation and solarisation, when we removed our people from these lighthouses, that we lost a connection with those coastal communities. But this particular initiative has facilitated us to reconnect with the various different communities around Ireland. So this collage shows an example of how we communicate and collaborate on the ground. We have our website, as I mentioned. We have on-site signage. They're both key marketing and communication tools. Training and mentoring supports. We develop storytelling toolkits for tour guides, and we do that using our archive so that we can bring the heritage to life using stories that really mean something. Annual reports, we produce those and we share those with stakeholders and most importantly potential funders, and we run a number of consumer campaigns and competitions to engage with target audiences, along with attending maritime events and festivals. So in terms of socio impact, in 2019 we conducted an independent socio-economic impact assessment of the Great Lighthouse of Ireland, and these are just some of the key statistics that I wanted to share with you. In 2019 we had, as I said, 15 experiences. We attracted over 420,000 visitors to lighthouses, delivering that 143,500 tower tickets. We had an estimated 4.92 million worth of direct spend in and around local communities in Ireland to do with lighthouses. And if you take the direct and indirect spend then to the regions, that totaled 16.86 million, and it supported a whopping 409 jobs. So lighthouse tourism, lighthouse heritage is in huge demand. It's delivering on our strategic all-island development agenda, and it's very much a catalyst for future investment. It would be remiss of me to stand up here in front of you all and talk about lighthouse tourism and not mention COVID. COVID triggered an unprecedented crisis in the tourism economy in Ireland, as it did everywhere else, and resulted in the immediate and immense shock to the sector. Challenges on the ground for us were temporary closures, loss of staff, maintenance issues given the nature of the buildings, and security. But our task as a brand partnership was to keep the brand alive and visible in the market, to build demand for when things opened up again, and help our partners not just to survive but prepare to thrive. A good example of how we did that was we went out to the market during COVID, and it was a signature project that we had. We launched Become a Young Story Keeper, which was a children's writing competition. And we had a huge response, over 1,300 entries, great market exposure, and it culminated in the printing of a beautiful book, which is illustrated here with lots of children's stories in it. We also published all of the 1,300 stories on an accompanying website, and we produced 10 videos which were published on YouTube as well. All of the proceeds of this book, by the way, went to a children's charity. And it was a great way of connecting with the market during COVID, but also stimulating a potential demand for when COVID ended and the lockdowns were all finished and people could get back to the lighthouses. What next then for the brand partnership? So, Irish Lights as an organisation, we want to continue to protect and share our unique built heritage. We want to leverage Great Lighthouse of Ireland to open new opportunities to deliver and add value in areas around engagement, public engagement, education and collaboration. And as I mentioned, we have an extensive archive that really is untapped at this stage, and we feel it presents significant opportunities to improve how we showcase our heritage and history into the future. So as part of planning for the future, we do a lot of consultation with various marine stakeholders and directly with tourism agencies, and our work has been informed by consultation with these people. In early 2022, our National Tourism Agency, Fáilte Ireland, commissioned some bespoke research to review international lighthouse and coastal activity tourism, and they identified a number of critical success factors: destination development, visitor orientation, eco and sustainable tourism, niche markets, and the concept of clustering. So the emerging concepts that we see in Ireland are using the lighthouses as a hub in terms of attracting people to remote parts of the island. We're looking at connecting blueways and greenways and trailheads, and we want to also, I suppose, explore centres of excellence around the likes of scuba diving, geology, immigration, in terms of how we build our interpretation for visitors. And then the final area is the premium experiences, and that relates to the accommodation. During COVID, obviously the lighthouse tourist, the visitor attractions weren't open, but the lighthouse tourist accommodation was, and it was phenomenally busy, really, really busy. And we've realised now that there's a big demand there for unique bespoke accommodation experiences, and it's something that we want to explore further. So in conclusion, just to say from an Irish Lights perspective, our experience in lighthouse tourism has been about harnessing the collective effort between communities, government agencies and tourism agencies, and it's about protecting and sharing Ireland's maritime history and culture, and it makes no sense if it doesn't deliver social and economic benefit in the coastal communities, and we've proven that it does, and we want to continue to do that. Thank you.
Alors, merci beaucoup.
Thank you very much, Dave, for that presentation, which I think is extremely interesting, and it shows that everywhere in the world, you know, we could have taken the easy way out and said, well, we have beautiful buildings, let's get people to come up into these buildings, let's get money from that, and then, you know, it's just basically a view. You go up a building and you see a view. But in fact, we realize that we've made the most of this culture, this heritage. We have said that a lighthouse is a connection between the land and the sea, that the people who live on Earth are extremely attached to lighthouses in the same way as sailors are. Perhaps not for the same reasons, but there's that strong attachment. And this dual nature of the lighthouse appeared in the 90s in France. Dave has told us what happened in Ireland. I think that we have become aware of the fact that we had something that was major, of major importance. It was something that would allow us to develop our territories, our local communities, and become a genuine stakeholder, become a genuine tool to learn more about our communities and about our heritage. And we're very fortunate because we have engineers who built fabulous works of art. And Nathalie told us a little bit earlier, she showed us the photographs of the Île Vierge lighthouse. And yesterday you visited the Cordouan Lighthouse, and you saw some major artistic features. And I'm not sure that today we would spend as much, devote as many resources to creating and developing these works. Remember, we need to do that because that is what we're going to be leaving for future generations. I think that we need to have this concern to focus on something that is both beautiful and functional, and we can connect both. And now, Jacques, I don't know where we stand. Do we have any time left for questions and comments? I am so sorry we have no questions. You're behind schedule. Oh, well, I'm very pleased to tell you that you have as much time as you like. No, you have as much time as you like to ask questions. Okay, go ahead, because before they change their minds, go ahead. You know, we're already supposed to have left the room, but anyway, no, we will take some time for questions. Hello, Bernard Maître. A question to Nathalie about the Île Vierge lighthouse. Well, isn't there some sort of a construction defect? Because I was very surprised to see that the joints were superimposed, so it's like a saber effect, and on top of it they are in cement, so it's not supple, it's not flexible at all, so it's not lime, I think there's an issue there with the construction using cement. Isn't that a factor? She said, is the fridge working? No, is the microphone working? The microphone. Well, in fact, the joints, no, they are not superimposed. It is a perfectly performed masonry with blocks. But the crack, however, is entirely vertical. It is between two blocks in the joint, and it cuts the block below it in half, and so on. So it's a vertical crack. But this was a very important point, the fact that the crack was capable of, it was an effort that was capable of cutting a kersanton, or granite block. It is rock that has a high resistance. I couldn't give you, well, in scientific terms, this is a rock that resists approximately 150 megapascal. So that might not be something that is relevant to all of us, but you see the standard concrete with which we build buildings every day, it resists to a common, what we use for buildings is approximately 20 megapascal. So it's between 20 and 150, so the best high-performance concrete will not achieve 150 today. So this Kersanton stone, which is from Brittany, which actually ages very well, it does not deteriorate over time, and even that was cut in half by the crack. That was the importance of what I wanted to emphasize. What was your second question? You talked about the cement joints. For granite, it's not shocking. We wouldn't do that with limestone, but we would use. But with granite, there's no problem in having cement. Several repair operations were undertaken on these joints. Perhaps another question, and then I suggest that on the boat or over lunch, You can, of course, ask all your questions and exchange views. If you want to go to Cordouan, of course, we have to go at the right time. We have to stick to the timing. Sorry, without the microphone, I can't hear. Is there another question, perhaps, from the room? Only those who have the Monday ticket will be going to Cordouan today. Others have the Wednesday ticket, and obviously you'll go on Wednesday. Are there any other questions? I think there's somebody at the back of the room there who wants to ask a question. Could we have a microphone perhaps at the back of the room? There's a question there. Solange, just stay here. Jean-Marie, stay. He has the microphone. Yes, hello, thank you. I'm Florie Allard. I'm working at the Regional Art and Culture Directorate, and I'm tasked with working on restoring the Cordouan Lighthouse. And I had a question for you concerning the work that you did in England on the way the project was organized and how you put it together. Who were the stakeholders, the different parties who were involved in your project? Is it just the university, or did you also work with the owners of the lighthouse?
Yeah, but the project was motivated by the UK and Irish GLAs, so we worked very much with them. We also had a partnership with several engineering consultants, initially from HR Wallingford and AECOM. Yes, so it wasn't just an academic study. It was definitely working under the supervision of the UK and Irish GLAs.
Oui, Omar.
Jean-Marie, the microphone for Omar. In front.
My name is Omar. I work with IALA, the International Association of Marine Age Navigation and Lighthouse Authorities. I have a question for Alison, triggered by the other question. So, the work you undertook was fueled by the fact that the lighthouse authorities were worried about the health of the lighthouse structures. So my question is, do you see these measurements being made all over the UK? Perhaps is there a case for a worldwide recommendation or guideline on how to measure vibrations in structures like that, and how to monitor the health of these structures?
Yes, and I did contribute to one of the IALA publications. So we're very happy for the methods that we developed to be used much more widely. The towers that we focused on were the interlocking blocks. And actually an interesting finding was that the wave impacts would have been sufficient to cause failure had it not been for the vertical interlocking element. And I know that in different countries, you don't necessarily have that interlocking mechanism. So I think we are okay from a UK and Irish perspective that those assets are not going to fail, at least for the next up until 2067. But we'd be very happy to talk to international authorities about their assets and what they might do regarding monitoring.
Thank you.
Thank you. Géraldine Delannoy, IALA Worldwide Academy. Thanks for the very good presentations. And I have a presentation for Serima. The replacement of the mercury, how long was in total the light out of order?
Le micro sur la table. Un mois, même pas.
There is no interruptions. No, between the replacement. It's okay. All is I don't know in English. Phased for the light continue to work.
Bon, je crois qu'on va arrêter les.
I think we're going to have to stop the questions here. You have 3/4 of an hour to eat, so you're really going to have to stick to this timing, because for those who are going to visit Cordouan, for them to be able to go to Cordouan. So please just go and have some lunch in the room next to this room. Thank you. All right, so the room is the Cordouan room. You have to leave the building, take the street on the left. The street on the left at the second crossroads, the building is at the bottom. For those who do not have badges or do not have their tickets, I remind you that you can get them at the reception desk. So please, we have to start again absolutely at 1 o'clock on the dot this afternoon right here. So please be back here at 1 o'clock. Enjoy your lunch and see you. And thank you to all the speakers and to all the people who asked the very interesting questions.